intelligence. Let's get started. Let's do a quick recap. What we had seen 2 days before in one of our videos. Um, Let me go ahead and share my screen. So we had seen the concept of entropy. How is it calculated? What is the mathematical formula behind it? How is it actually used to measure the disorder or the purity of a particular node? We had seen for this particular split, how is this the mathematical formula of entropy is used to calculate the entropy of each of the nodes, that's F1, F2, and F3. And we had also seen what is a pure leaf node. When you have 0 nodes and 5 years, this is actually a pure leaf node. The purity this is absolutely a pure node, and we saw why leaf node is actually not needed to split much more further. We had also seen how we actually split a decision tree. What is the patterns we can follow? We had discussed each of those patterns. And after this, we had also see which pattern to select to split a decision tree is actually governed by a concept called information gain. We had seen the formula of information gain. We also saw how the information gains for the split pattern is actually calculated, and we have also seen that for other patterns we also try to calculate the information gain and try to see from which pattern of split we are getting the maximum amount of information gain. So in that basis, the decision tree is actually constructed. Now let's take a deeper dive to what we discussed in entropy further ahead. Let me take a very simple business problem here. You have F1, F2, and F3. These are my features, and there is one output variable. And F1 has categories like C1, C2, and C3. Same goes with F2 and F3. Now let me try to construct a decision tree on basis of feature F1. If I just take F1 here, and if you see F1 has 6 yes and 3 no's, and let me just split this into C1 and C2 over here. And C1 has 3 yes and 3 no's, and C2 has 3 yes and 0 no's. We had seen why is this actually called a leaf node? Because it has 0 no's here, and it's a pure split. And we had seen why the pure split entropy comes at 0, and we will also see like why the entropy of this particular C1 node is coming as 1. If we recall the formula, the mathematical formula of entropy, it was minus p plus log to the 2p plus minus log p minus log to the base 2 p minus again. Now let's try to put this for C2. Now, if you recall, the p plus is nothing but the probability of yes over here. So if I want to calculate the probability of yes over here, that's nothing but 3 divided by 3. Why is 3 divided by 3? So there are 3 yes, and the total number of events is here 3. So that's nothing but 3 divided by 3 log 2 divided by 3 divided by 3 minus the probability of no. What would be the probability of no for C2? That's nothing but 0 divided by 3 and log to the base 2, 0 divided by 3. If you calculate this, this will come as 0. And we call this as a 0-bit node. Whenever any node we get entropy as 0-bit, it is considered absolute pure node. And that is the reason we are calling this as a leaf node. It doesn't require splitting further. Let's do the same with C1. Let's try to calculate the purity of the C1 node. Now for C1, if I quickly put this formula, you have 3 yes and 3 no's. So the probability of plus even, that's nothing but the probability of being yes. What will be the probability of yes? It's nothing but 3 divided by 6. That's 3 plus 3. The total number of events are 3 plus 3. That's 3 divided by 6 log to the base 2, 3 divided by 6. Again, the probability of no, it would be same, right? Because you have 3 no's. So 3 divided by 6 log 2. Now, if we calculate this will nothing be but 1. There's a 50% probability for your P plus. 50% probability means what? Like there's a 50% probability is 3 by 6. There's a the probability of yes and the probability of no is 50% over here. That is where you tend to get the entropy as 1. Now let's take a step back now. Let me try to plot, let's try to see how do we plot entropy with probability. Probability is nothing but the probability of yes and no's. Let's do a let's take this to the next tactical level. Now, if I want to plot, entropy versus probability, this could be anything. This could be probability of P is nothing but probability of plus and probability of minus. That means the probability of yes and probability of no. Now, if you see, this is a very important intuitive concept, and this is very important to understand if someone is asking you, what exactly, how do you actually plot entropy with probability? It's a very frequently asked interview question as well during your machine learning interviews. Now, if I do this, you can see this typical graph. The entropy actually increases as your probability of P plus is increasing, and it reaches the maximum level. Like the entropy would be highest when the probability of both the outcomes are equal. That's when your probability is 0.5. And that is what we saw, right? That is what we saw here. So the probability of yes was 3 divided by 6. That's 50% probability. And probability of no was even 3 divided by 6. That is where the probability becomes 1. Now, again, if your probability of P plus, increases after this, again, the probability, your entropy will decrease. And when it is at, it is at 1, when the probability of, P plus, that is nothing but your yes is 1, your entropy again becomes 0. Let's see that, we saw that, right? So your probability of P minus here is basically a 0 bit over here. And if we see this, again, your entropy is becoming, 0 over here. So that is how the entropy is actually, plotted against a probability. This is a very fundamental concept. Let's take a step higher than this, and let's see why the concept of Gini impurity again comes, because we are happy with computing the entropy, the purity of the node with entropy. Why do we need Gini impurity then? So it's totally built on the same concept. Like Gini impurity also checks uh, the basically the purity of the node. So this is what we were calculating, right? So let's do the same computation for using Gini impurity. Let's first look into the mathematical formula of Gini impurity. It's pretty much simple. It's 1 minus, if it's sum over 1 to n, and the probability square. Now, if I just break this down, this is nothing but probability of plus square plus probability of minus. Probability of plus is nothing but the probability of yes and probability of no's over here. Now, if I quickly put this for my C1 node here, so the probability of plus would be how much? It's nothing but 3 divided by 6 plus the probability of no. That's 3 divided by 6 again. Now, if I just sum this up, this 0.25 plus 0.25, 1 minus 0.5, that is nothing but 0.5. So can you note a difference here? If we calculate entropy over here, this was coming as 1 for C1 node. And if we calculate the Gini impurity of C1, it's coming as 0.5. Similarly, if you do this for Gini impurity for C2 here, it will come as 0 as well. I mean, it's just put it in this formula. You can try it, 3 divided by 3. I mean, this will come at 0 if you calculate it for C2. Now, can you notice the difference? The entropy over here is 1 and the Gini impurity is 0.5. Now let's again plot what we did before. We had seen, how do we plot entropy with against probability. Now what we will do, we'll plot both. We'll plot both entropy and entropy and Gini impurity with respect to probability. Now, if we do that, you can actually see, this is nothing but the probability part. So your x-axis, your probability, and your y-axis has both entropy and Gini impurity. So here is the difference. Like the maximum value which entropy reaches at zero point 0.5 probability would be 1. On the other hand, if I plot Gini impurity, the maximum value which Gini impurity reaches is zero point 0.5. And then it again start decreasing to 0 over here. Same trend like with entropy. The only difference is the maximum amount of value which Gini impurity reaches is zero point 0.5. This is a very fundamental interview question. If someone asks how Gini impurity is different from entropy, you need to explain this. You just need to remember this particular graph. Just remember that on your x-axis you have your probability, and your y-axis you have your entropy and Gini impurity. Just remember one thing, that when the probability is 0.5, then the maximum value reached by Gini impurity is always 0.5. So your Gini impurity would always range between 0 to zero point 0.5, and your entropy would always range between 0 to 1. So question is like, why to use Gini impurity then? Like what is the basic use then? Um, if you see in most of the ensemble techniques, like your random forest or your XGBoost machine learning algorithms, Gini impurity is always taken as a parameter instead of entropy, and there's a reason behind it. If you see, Gini impurity is computationally more efficient, as there is no logarithmic calculation in case of Gini impurity. Why? Let's go to that formula again, the basic mathematical formula. Do you see any logarithmic calculation over here? There is no logarithmic calculation. It's a very simple formula. 1 minus probability of plus to the square plus probability of minus to the power square. Straightforward formula. Obviously, the computational power or the computational efficiency of Gini impurity is much more better than entropy. The reason is, I'll tell you the why. Again, let's go to the entropy formula. See, there's the entropy formula, right? This was the basic mathematical formula of entropy, right? You have a logarithmic calculation over here. You have a log base to the power, log plus p plus. So if you do any logarithmic calculation, obviously the computation would be a complex one if you compare with this formula, right? If you compare it with this formula. So this is why Gini impurity is much more computationally more efficient, as there is no logarithmic calculation, and it acts as a parameter for most of the ensemble techniques. We won't even use machine learning for even classification or regression, for your random forest or XGBoost. And we have seen, right? With Gini impurity and entropy, after we calculate that, we always use the information gain to understand what is the pattern of the split. So I hope this is again this is a very frequently asked question: why Gini impurity is preferred over entropy in machine learning? So always remember the concept that it's computationally more efficient. Remember the formula. There's no logarithmic calculation, and always remember this particular graph. So you just need to explain the interviewer that this particular graph. So if we plot the probability, and in a y-axis it's entropy and Gini, this is how they actually behave. So remember this graph and the basic computational formula. You don't need to remember the exact formula, but just you need to understand that make the interview understand that there is no logarithmic calculation in case of Gini impurity when you compare it with entropy. I hope this video was useful, and in the next video we will be seeing, we had seen categorical features, right? For how do we calculate it for categorical features, but we'll see how the decision tree actually works for numerical features as well. We will do a deeper dive, and we'll understand how it actually acts for a numerical feature split in the coming videos. But I'll do a quick recap as well. This particular aspect, what we discussed, right? We will see how F1, F2, if F1, F2, and F3 are numerical features, how is entropy actually calculated? And we'll do a deeper dive to that as well. Thank you so much. I hope you enjoyed this video and it was useful to it. I mean, useful for your interviews. If you like the video, please do subscribe to my channel. I'm looking forward to talk to you soon. Thank you so much.